Hello and welcome to Pros and Experts. Let us do the next problem. An LTA system has h of t such that L of h of t equal to h of s equal to 1 by s plus 1 and real part of s is greater than minus 1. Determine the system output y of t if the input is x of t equal to e to the power minus t by 2 plus 2 e to the power minus t by 3 e of t. Okay, so the question gives the transfer function h of s equal to 1 by s plus 1 and the real part of s greater than minus 1 means it is nothing but the ROC and it indicates that this system is causal, and there is no other relevance to this question. I think so. Okay, let us see. And the question asks to find the system output y of t and given input as the signal. Okay, so this is a comparatively very simple problem. Let's start solving this. So first given h of s is equal to 1 by s plus 1 and ROC is given. If it is needed, we will take it. So h of s is given. Now the input signal x of t is given, not the transform, but x of t is given as e to the power minus t by 2 plus 2 e to the power minus t by 3 u of t. Okay, so this has two terms and both the terms are in the form e raised to at u of t, whose Laplace transform, you know, it would be a very popular Laplace transform, this is 1 by s minus a. Okay, with the ROC sigma greater than a. Okay, so we can right away find x of s, the Laplace transform of the input signal, which is, what is the Laplace transform of e raised to minus t by 2 u of t? It should be 1 by s plus half. Okay, plus 2 times, what is the Laplace transform of e raised to minus t by 3? It is 1 by s plus 1 by 3. Okay, so now the question is to find out the output y of t. Okay, output y of t. So what is the procedure? We know y of s is equal to x of s into h of s, or h of s into x of s. It comes out from the convolution property of Laplace transform. So that implies y of s is equal to, we can multiply both h of s and x of s. So this 1 by s plus 1 into h of s into x of s. X of s is 1 by s plus half plus 2 by s plus 1/3. Okay, and if I take 1 by s plus 1 into the bracket, I can write it as 1 by s plus 1 into s plus half plus 2 by s plus 1 into s plus 1 by 3. Okay, now the question is to find the output y of t in time domain. But what we got the output is in Laplace domain. So we have to start steps to make it into time domain or calculate the inverse Laplace transform. For that, the first thing you have to do is make it a partial fraction. You know, it is partial fraction, and we have here two terms. I can separately find the partial fraction of these two terms. So suppose I'm first calculating the partial fraction of this term. Now we have in several problems learned how to make a partial fraction, how to find the constants a, b, c, etc. But in this problem, let me tell you a very simple method of making partial fractions. Okay, first I am taking this term and finding the partial fraction. You know, partial fraction is equal to, suppose, partial fraction is equal to, you listen very carefully, 1 by big number minus small number. Okay, this is a thumb rule. Okay, 1 by big number minus small number into 1 by s plus small number minus 1 by s plus big number. If you follow this expression, this thumb rule, you can very easily find out the partial fraction of any term. That is equal to 1 by big number minus small number. What is big number in this? Is it 1 or is it half? 1 is the big number, so 1 minus half into 1 by s plus small number, which is s plus small number. S plus half is s plus small number, right? So 1 by s plus half minus 1 by s plus big is s plus 1. Okay, this is listen, this is the partial fraction expansion for this term alone. Okay, plus 2 into, okay, 2 into, in a similar way I can make the partial fraction out of this term also. So again I can guide you this, right? Okay, 1 by big minus small, which is big minus small. We have 1 and 1 by 3 here, so 1 minus 1 by 3 into 1 by s plus small, s plus 1 by 3 minus 1 by s plus 1. Okay, now let us simplify. This is 1 by 1 minus half is 2 into 1 by s plus half minus 1 by s plus 1 plus, what is 2 into 1 by 1 minus 1 by 3? It should be 3, right? So 3 into 1 by s plus 1 by 3 minus 1 by s plus 1. Now look at all the terms. All the terms are non-Laplace transform. So it is very simple to calculate the inverse Laplace transform by observing. Okay, therefore y of t is equal to, finding the inverse transform, 2 into, what is the inverse transform of this term? It should be e raised to minus t by 2. Okay, into u of t minus, this 2 is common, so 2 into, what is the inverse Laplace transform of 1 by s plus 1? It is e raised to minus t of t. Alright, now what is the Laplace transform, inverse Laplace transform of 3 by 1 plus 3 by s plus 1 by 3? It is 3 into e raised to minus t by 3 u of t minus 3 is common, so minus 3 into inverse Laplace transform of 1 by s plus 1 is again e raised to minus t u of t. Okay, I think it is possible to simplify it further. That implies y of t is equal to, we have obviously two terms having e raised to minus t of t, so we can write it as minus 5 e raised to minus t u of t plus 2 e raised to minus t by 2 u of t plus 3 e raised to minus t by 3 u of t. So this is the output y of t, and that's our final answer. Okay, I think you're ready to solve the next question. Find the Laplace transform and ROC of the following signals. This is a 9 marks question. First question is e raised to minus a mod t. Second question is sine omega 0 t minus b e to the power minus a t u of t, and b are real constants. Okay, first let us solve question A. The signal to be evaluated under the Laplace transformation is x of t equal to e to the power minus a mod t. But you already know, we have already discussed, defined that mod t is equal to t for t greater than or equal to 0 and minus t for t less than 0. You can make use of this definition for mod t. Therefore, e raised to minus a mod t will be equal to e raised to minus at for t positive and e raised to plus at for t negative. Okay, so let us apply this and find out the Laplace transform for e raised to minus a mod t. Now we will start from the scratch. The definition of Laplace transformation is x of s is equal to integral over minus infinity to plus infinity the signal into e raised to minus st dt. Okay, so let us apply this integral definition over our signal e raised to minus a mod t. But you can see that our signal is valid. Okay, our signal is valid for two different time intervals. Okay, for positive time axis and negative time axis. Okay, So we have to split our integral accordingly. So I'm splitting this integral from minus infinity to 0 for including what? For including negative t. Okay. And okay, so what is the integral at this negative side? You know, the definition is x of t into e raised to minus st dt. What is x of t at negative time? This is negative time. So x of t at negative time is e raised to at. Okay. So instead of x of t, I can write e raised to at. The rest is e raised to minus st into dt. Okay. So instead of x of t, I'm writing e raised to at. Okay, e raised to at here. The integral is not over. Plus, now we have to bring the positive time values. For that, the integral will be from 0 to plus infinity. Okay, I think the idea is clear. So integral 0 to infinity stands for the positive time axis. So in that case, what is x of t? We are actually introducing this definition in this integral. Okay, so this integral should be followed by x of t. And what is x of t at t greater than 0? It is nothing but e raised to minus at. So instead of x of t, I can write e raised to minus at. Okay, the remaining is e raised to minus st into dt as per the definition. Right? Now, this is equal to, I can write it as e raised to a minus s into t. We can club the exponents together, plus integral 0 to plus infinity e raised to, I can write as e raised to minus of s plus a into t dt. Okay, okay, fine. Now we can find out the integral. So the evaluation result of this integral is e raised to a minus s into t divided by a minus s. Okay, within the limits minus infinity to 0, plus evaluating the second integral, you will get e raised to minus of s plus a into t or divided by minus of s plus a within the limits 0 to infinity. Okay, so that is equal to now what we have to do is we have to apply the limits. Okay, so first we can apply the upper limit here, which is 0. So what happens when we apply the upper limit? It becomes e raised to 0, which is 1. Okay, so I can write I can take out a minus s, 1 by a minus s. So when we apply the upper limit, we get it is e raised to 0, 1. Okay, minus now what happens when, okay, let me save some space. Okay, what happens when you apply the lower limit? Lower limit is minus infinity, so it becomes e raised to a minus s into minus infinity, right? E raised to a minus s into minus infinity here instead of t. So what is this? It is like e raised to something into minus infinity. That is e raised to minus infinity is 0, right? So we can write 0 here. Is that clear? Can you really write 0 there? Just think twice before writing 0 there. Is it always 0 there? We have to take care that this value is 0. Okay, this value here must be 0 only if a minus s is a positive value, right? Only if I think here it is 0 only if a minus s is a positive value. I will tell you why. Because if at all if a minus s is a negative value, say minus 1, what happens? E raised to minus 1 into minus infinity will give you e raised to plus infinity. And if you apply and if the integral limit results in e raised to infinity, this whole term will never exist. Okay, so this whole integral will not exist, whole Laplace transform will not exist. Okay, so in order for our Laplace transform to exist, we have to make this assumption that while applying this lower limit, this a minus s should be positive. Okay, a minus s should never be negative, it should be positive. Okay, that's our assumption here. Okay, now if a minus s is positive, we can be sure that this application of this lower limit results in 0 over there. Okay, so e raised to some positive value into minus infinity results in e raised to minus infinity for sure, and that is 0. Hope you are clear with this. Plus, okay, the next term we can again apply the limits. 1 by s plus a. While applying the limits, it becomes e raised to what will result if you apply the upper limit in e raised to minus s plus a into t? It is e raised to t is infinity, so e raised to minus infinity. Again, you can get 0. Again, are you sure is it 0? If it is 0 only if, I can write it 0 only if what is the assumption I have to make? The assumption is s plus a should be positive. Okay, we have to be very attentive. If at all s plus a is positive, then you substitute infinity here, you will get e raised to minus infinity and you will get 0. Okay, but what if s plus a is negative? What if s plus a is negative? If s plus a is negative, say some value minus 1, what happens is e raised to minus into infinity, that is e raised to plus infinity. Again, this part of the integral goes unbounded, infinite, so the entire Laplace transform will not exist. So for us to make sure that this Laplace transform exists, this term should be, insertion of this upper limit should give you 0, and for getting 0 here, we have to make sure that s plus a is positive. That's why I am assuming that s plus a is greater than 0 here. Okay, so under these two assumption, I can write it as 0 here and minus. What happens when you insert the lower limit? It is e raised to 0 will give you 1. Okay, now you can again simplify this as this is equal to 1 by a minus s. Okay, 1 by a minus s. I'm denoting in bracket this condition. What is a minus s greater than 0 means? It means a greater than s, right? Means a greater than s or s less than a, right? S less than a. Okay, plus the second term becomes minus and minus becomes plus. So plus 1 by s plus a, plus 1 by s plus a. Again, we have a condition here. S plus a is greater than 0. What is s plus a greater than 0 means? Means s greater than minus a. Okay, so the final answer, the Laplace transform of e raised to minus a mod t is nothing but 1 by a minus s plus 1 by a plus s. I can write it a plus s. And here, what is s less than a? S means it is a complex frequency given by sigma plus j omega. Less than a is a real value. The question is clearly given as a as a real value. So I can write a plus j0. Its imaginary part is 0. So comparing sigma will be less than a. Okay, so I can write it as sigma less than a for this term alone, and for the next term, what happens is s greater than minus a means sigma plus j omega greater than minus a plus j0. Okay, on comparing the real parts, sigma greater than minus a will be the result. Sigma greater than minus a. Okay, so again, what is 1 by a minus s plus 1 by a plus s? I can simplify it as taking the LCM, it is a plus s plus a minus s by a square minus s square, right? That is equal to 2a by a square minus s square. Okay, and whenever you write Laplace transformation, be note carefully that you have to express its ROC also. Okay, you have to write its ROC also. And what is ROC? You have sigma less than a. Okay, sigma less than a for this term and sigma greater than minus a for that term. So if you have two individual terms and two individual ROCs, what is the total ROC? total ROC for the total signal, it should be the intersection of these two ROCs. Okay, and let's see what will be the intersection of these two ROCs. I can draw in a rough manner here. Sigma less than A. Sigma is in the real axis. Okay, this is j omega. This is S plane. Okay, sigma is in the real axis. So sigma less than A means I'm supposing A is a positive value and A is here. Okay, and this is minus A, right? So I'm supposing that sigma less than A will be like this, the whole portion in the plane less than A. Okay, and that's the ROC for the first term, and for the second term it is sigma greater than minus A. Okay, for the second term it is sigma greater than minus A. So it would be something like this. So entire S plane where sigma is greater than minus A. And now I have already told you the ROC for the total signal. Yes, the total signal, this transform is nothing but the intersection or the common area between these two individual ROCs. And what is the common area? It is nothing but this area. Okay, this area means this area is minus A less than sigma less than plus A. Okay, so ROC is minus A less than sigma less than A. So this is the final answer. And now there is one more sub question left behind, which is to find the Laplace transform of sine omega 0 t minus b into e raised to minus at of t. Okay, so I think we know the standard result, which says Laplace transformation of sine omega 0 t will be equal to omega 0 by s square plus omega 0 square. Okay, this is an important result that you need to by heart. Similarly, Laplace transform of cos omega 0 t will give you s by s square plus omega 0 square. Okay, and maybe you have to remember one more property of Laplace transform, which says that if x of t has a Laplace transformation x of s, then e raised to minus at x of t, okay, e raised to minus at x of t will give you frequency shift. Okay, frequency shift, which is nothing but x of s plus a. You have to take note of the sign conventions also. If it is e raised to minus at, the shift will be s plus a. Okay, so if you know these three relations, it's very simple to solve this. So our x of t is given as sine omega 0 t minus b into e raised to minus at of t. Let me take sine omega 0 t minus b. Okay, I'm just taking sine omega 0 t minus b. So what is the Laplace transform of okay, wait, I can proceed in a different way. Sine omega 0 t minus b. What does sine omega 0 t minus b? We know that sine of a minus b. Okay, sine of a minus b is equal to sine a cos b minus cos a sine b. Right? Applying that relation, that trigonometric relation, we can write it as sine omega 0 t into cos b. Okay, similar to sine a cos b minus now what is the relation cos a into sine b. Okay, cos omega 0 t into sine b. So this is what you get if you expand sine omega 0 t minus b using the basic trigonometric identities. Okay, now what is the Laplace transform of this thing, sine of omega 0 t minus b? It will be the Laplace transform of whatever you see in the RHS also. Okay, so that will be equal to Laplace transform of sine omega 0 t into cos b. Okay, minus Laplace transform of cos omega 0 t into sin b, right? That is equal to, what is the Laplace transform of sin omega 0 t into cos b, the first term? Here you can see cos b is a constant. Okay, a and b are element of R. So cos b is a constant. You can take it outside the Laplace transformation because sin omega 0 t is the only signal here, because it contains a t. It is a function, it is a variable, it is a signal. Okay, so I can take cos b outside. Then what is the Laplace transform of sin omega 0 t? Or I can write one more step, no problem. Sin omega 0 t, okay, minus, in the second term, what is the constant? Sin b is the constant. Okay, so you take sin b outside, sin b into Laplace transform of sin b into Laplace transform of cos omega 0 t. Cos omega 0 t is the variable here or signal here. Okay, that implies Laplace transform of sin omega 0 t minus b equal to cos b into, what is Laplace transform of sin omega 0 t? We know it is omega 0 by s square plus omega 0 square minus sin b into, what is Laplace transform of cos omega 0 t? It is s by s square plus omega 0 square. Okay, now we got the Laplace transform of sin omega 0 t minus b. That means sin omega 0 t minus b into u of t. Okay, I'm so sorry, I've forgotten to write u of t here. Actually, this is Laplace transform of sin omega t into u of t. Okay, it is understood that it's a unilateral Laplace transform. So maybe we can write u of t to specify it. No problem. Okay, so we have the Laplace transform of this part, sin omega t minus b into u of t. Okay, therefore, now using this property, we can conclude that Laplace transform of e raised to minus at into sin omega 0 t minus b u of t will be equal to, what difference does it make? You can see that if you are multiplying e raised to minus at with the signal, then the original Laplace transform x of s becomes x of s plus a. That means wherever you find s, you replace s by s plus a. It's a very simple procedure. Okay, so you can find s in this term like x square, and here it is s here and s square here. So replace all s by s plus a. Okay, so this is omega 0 into cos b by s should be replaced by s plus a. So s plus a square plus omega 0 square minus in the next term, the numerator has s into s plus b. S into sin b. Sorry. Okay, s into sin b. So s should be replaced by s plus a. So s plus a into sin b whole divided by, again there is an s here. So s plus a the whole square plus omega 0 square. So this is the final answer, final Laplace transformation. Okay, we will concentrate on the next question. This is a very good question. Let f of omega equal to f of t. That means Fourier transform of f of t. Determine the Fourier transform of g of t equal to f of at minus b in terms of f of omega. Right? G of omega should be found out in terms of f of omega, where a not equal to 0 and a b are constant, real constants. And handle the cases for a greater than 0 and a less than 0 separately. Okay, so the question says that you have a signal f of t. Okay, you have a signal f of t whose Fourier transform is f of omega. Okay, now you have a second signal g of t, which is obtained by from f of t as f of at minus b. Okay, f of at minus b, and the question is to find out g of omega in terms of f of omega. Okay, so it's a good question. So logically, finding out the Fourier transform of g of t, that is g of omega, will be equal to finding out the Fourier transform of this signal, right? Since g of t is equal to f of at minus b, g of omega will be equal to the Fourier transform of this signal. Okay, so what will be the Fourier transform of? Our aim is to find, I can write, our aim is to find the Fourier transform of f of at minus b. Okay, what only you know is Fourier transform of f of t is f of omega, nothing else. Okay, so your aim should be deriving f of at minus b from f of t. Okay, so you have to find, as a first step, you have to find or express f of at minus b from f of t, because you know only the Fourier transform of f of t. Okay, so do you have any intuitions? F of at minus b from f of t. Have you heard of this anywhere? We have seen in the first module, the basics of signals, that to get f of at minus b from f of t, you can see there are two signal operations. One is shifting and one is scaling. So the first thing that comes to your mind should be the precedence rule. Very good, the precedence rule. And the precedence rule states that if both scaling and shifting occurs in a signal processing, first thing should be shifting, then scaling. Okay, first shifting, then scaling. So now listen very carefully, be very attentive. You know, what you know is f of t has a Fourier transform f of omega. F of t has a Fourier transform f of omega. So to get f of at minus b from f of t, the first step should be finding f of t minus b, shifting first, right? So f of t minus b will be having, what will be the Fourier transform of f of t minus b? You know, this is time shifting. Okay, so time shifting results in multiplication with exponent in the frequency domain. So e raised to minus j omega b into f of omega. I can write the reason as because it comes under time shifting property of Fourier transform. You have to refer the time shifting property of Fourier transform. Okay, now ultimately what we have to get is f of at minus b. So you already have f of t minus b. Now what is f of at minus b? What will be the Fourier transform of f of at minus b? It should be, you have to be thorough with the scaling property. If x of t has a transform x of omega, then x of at will be having a transform 1 by mod a x of omega by a. Okay, let's make use of this property. So f of at minus b will be having a Fourier transform 1 by mod a into the Fourier transform of the, the Fourier transform we have obtained in the previous step. Okay, so 1 by mod a into e raised to, or is it the Fourier transform as such? No, it is x of omega by a. 1 by mod a into x of omega by a. So you have to scale every omega by a. Omega by a into f of omega by a. This is a b also here, right? E raised to minus j omega b becomes, just replace omega with omega by a. There is no any change. Okay, right. So f of omega by a into e raised to minus j omega b by a into 1 by mod a. So this should be the result. But in the question they have asked us to handle the cases for a greater than 0 and a less than 0 separately. That's a simple thing. So this is the actual transform. Now we can handle a greater than 0 and a less than 0. What is mod a for a greater than 0? Mod a will be a itself for a greater than 0. Okay, so for a greater than 0, I can write the Fourier transform of f of at minus b as 1 by a, because mod a equal to a, e raised to minus j omega b by a into f of omega by a. This is one answer for a greater than 0 case. Okay, now the second case is for a less than 0. So what is mod a for a less than 0 is minus a. We have seen this definition in the previous question, right? So mod a will be equal to minus a for a less than 0. So I can write in this case Fourier transform of f of at minus b will be equal to, instead of 1 by mod a, we have to write 1 by minus a. That is minus 1 by a into e raised to minus j omega b by a into f of omega by a. So this is the answer to the case where they have asked for a less than 0. So we have handled the both cases separately. And now we will see the next question. Explain the Dirichlet's conditions for the existence of Fourier transform of a continuous time signal. So they are asking the Dirichlet's conditions. There are certain conditions called Dirichlet's conditions. Only if at all a signal obeys these conditions, then only the Fourier transform of that signal exists. Otherwise, the Fourier transform of that signal cannot be obtained. Okay. So there are three conditions, Dirichlet's condition. The first one is, the most important one is, the signal whose Fourier transform is to be obtained, that signal must be absolutely integrable. Absolutely integrable. Okay, that's the first condition, Dirichlet's condition. That means if x of t is the signal on test, then the signal should be integral minus infinity to plus infinity mod x of t in dt should be a finite value. Okay, if your signal is absolutely integrable, then only the Fourier transform of that signal exists. Right? So absolutely integrable or absolute integrability means nothing but the area under the signal. Right? This integral is nothing but the area under the signal should be finite. That means the signal should never be unbounded like this. If you have e raised to at dt or e raised to at signal for a is greater than 0, the signal would be like this. Right? So as t tends to infinity, the area of the signal, area under the signal is infinite, is going to infinite. So such signals will never have Fourier transform. Okay, that's the first condition, signal must be absolutely integrable. Okay, the second Dirichlet condition is the signal to be transformed should have finite number of discontinuities. Finite number of discontinuities. Okay, if at all you have a signal like this, okay, here it is a discontinuity, right? Here it is a discontinuity. Again comes another discontinuity. Then comes next, and this goes to infinity. So in a given time slot, you can see an infinite number of discontinuities in the signal. Okay, so such signal will never have Fourier transform. Okay. Then the third, last condition is the signal which you are trying to get the Fourier transform should have finite number of maxima and minima. Finite number of maxima and minima. Okay. So consider a signal like this. Okay. So it has a maxima here, then a minima here. Again maxima, minima, maxima, minima. It goes like this, right? So we can see that in a specified, in a particular time slot, we can see a large number, infinite number of maxima and infinite number of minima on the signal. So such signal will also do not possess a Fourier transform. Okay, so these three are the Dirichlet's conditions for the existence of Fourier transform. Okay, let's jump to the next question. Determine the complex exponential Fourier series representation of the signal x of t equal to cos 4t plus sin 6t. So I have already told you in some previous videos that when exponential Fourier series representation is asked, okay, exponential Fourier series representation is asked for certain signals like sinusoids, cosine, or exponential, complex exponential, sine, cosine, or complex exponential, I recommend you to do the method of inspection. The method of inspection, which will give you the answer very quickly and very easily. Okay, so we will adopt the method of inspection here. So what is the method of inspection? The method of inspection advises you to compare the given signal x of t and the Fourier series representation of any signal x of t and arrive at the conclusion about x of k, the Fourier series coefficients. Okay, let us do this. Let me start with the expression for any continuous term periodic signal x of t can be represented as Fourier series coefficients by the equation sigma over k equal to minus infinity to plus infinity. Any signal can be represented like this: the x of k, the Fourier series coefficients, into e raised to plus j k omega 0 t. Okay, so since there is an omega 0 coming here, right, omega 0 coming here, I have to find the omega 0 from the given signal. Okay, so let me take temporarily our given signal x of t equal to cos 4t plus sine 60. Okay, so how will you find out the omega 0? Omega 0 is nothing but we can adopt the very simple method, HCF of 4,6 divided by LCM of the denominator. This 1. There is no denominator here. Okay, so HCF of 4,6 is 2. Definitely it is 2. So omega 0 will be equal to 2 radians per second. Okay. So having a knowledge about the omega 0 of the given signal, I can again write the signal as x of t equal to sigma over k equal to minus infinity to plus infinity x of k into e raised to j k into 2 into t, because omega 0 equal to 2 we have found it here. Okay, so let me denote this equation as equation number 1. Okay, so what my equation 1 tells me is you can express this signal given in the question in this format, and this is a universal format given by the Fourier series expansion. Okay, so let equation 1 stay there for some while, and now I am taking our question signal x of t is equal to cos 4t plus sine 60. However, our method is having a name method of inspection. So this signal, I'm pretty sure that this signal should be compared with this signal because both the signals are same. Okay, so for that, however, I have to change the signal into some format given in equation number 1. Okay, so equation number 1 has a complex exponential term. That's the signal here. So I have to convert cos 4t and sine 60 in terms of complex exponential. Is it possible? It is very simply possible. So I can change x of t as, what is cos 4t? Cos 4t is 1 by 2 into e raised to j 4t plus e raised to minus j 4t. I have already told you these are some magical equations in signal science systems, because very number of complex problems can be solved using this magical equation. So similarly, what is sine 60? Sine 60 is 1 by 2j into e raised to j 60 minus e raised to minus j 60. Okay, right, now I can again simplify it as x of t equal to half e raised to j 4t plus half e raised to minus j 4t plus I ask you not to forget 2j component in sine 60. Okay, whenever sine is expanded, you will have a 2j component here, but cos will be having only 1 by 2 here. Okay, so expanding the next bracket, 1 by 2j e raised to j 60 minus 1 by 2j e raised to minus j60. Okay, now what I'm doing is let me take this term first. Okay, so this is minus 1 by 2j into, okay, e raised to minus j60 is, I can write as e raised to plus j into minus 3 into 2 into t. Does that make sense? Right, it is still it is e raised to minus j60, but I am writing e raised to minus j60 in this fashion, in this particular fashion, for some reason. Okay, plus what is the next term? This term. Okay, so that implies 1 by 2 into e raised to minus j40. I am writing it as e raised to j into minus 2 into 2 into t. That will be right. Still it is e raised to minus j40. Okay, plus what is the next term? Now I am going for this term, that is 1 by 2 into e raised to, I can write as j into 2 into 2 into t. Okay, plus finally this term is 1 by 2j into e raised to j into 3 into 2 into t. That is e raised to j60. Right? Now, why I have written like this, you will get to know. Because actually I'm comparing this equation we have already got here with equation number 1. So what is common in both these equations? In both these equations we have one complex exponential term, right? This is the complex exponential term, or in other words I can say this is our signal. Okay, this is our signal, because there is a t here. T is the variable, t is the function, so this term is the signal here. Okay, and now you have to be very thorough with this concept that whatever is multiplied with this signal, that means x of k, right? X of k is being multiplied with this signal. X of k is not a signal. Why? Because x of k is nothing but a scalar value. It does not have any function t here. T is the variable, so this is the signal. Okay, so whatever is the coefficient of this signal is x of k. Okay, so that the same strategy I'm going to follow in this equation. You have to spot signal in every term, and whatever be multiplied with this signal will give you x of k. Okay, this is x of k. So the coefficient of the signal will give you x of k. And what is the value of k? That every term will give you its own value of k. How? It is nothing but you have to compare e raised to jk to t with e raised to j into minus 3 into 2 into t. What does that give you? It gives that comparing this term alone and this signal alone will give you k equal to minus 3. Right, e raised to jk to t and e raised to j minus 3 to t will give you k equal to minus 3. So this term corresponds to, this entire term corresponds to, I can write it as this entire term corresponds to k equal to minus 3. Okay, so what is x of k? Now x of minus 3, right? X of k is now x of minus 3 because k equal to minus 3. And what is x of minus 3 now? X of minus 3 or x of k is the coefficient of the signal, that is the coefficient of signal. What is the coefficient of signal here? This is signal. What is the coefficient? Minus 1 by 2j. So we can pretty surely write that x of that implies x of k or x of minus 3 is equal to minus 1 by 2j. Right? That is what the first term gives you. Okay. Similarly, what does the second term gives you? Second term, this is the signal. So this is x of k. 1 by 2 is x of k. And what is k here? E raised to jk to t. Here e raised to j minus 2 to t. So k equal to minus 2. So this term will give you k equal to minus 2. Okay. So I can write x of minus 2 is equal to the coefficient of the signal, that is 1 by 2. So x of minus 2 is equal to 1 by 2. Okay. It's simple. Now what is the next term giving you? The next term gives you x of k as 1 by 2 because 1 by 2 is the scalar here. The other term is signal. Okay, this is a signal, this is the scalar. So x of k is 1 by 2. And what is k here? K is equal to 2 e raised to j k omega 0 t. Okay, so this term corresponds to k equal to 2. Therefore, x of 2 will give you 1 by 2. Okay, and finally the last term gives you a k equal to 3. Okay, k equal to plus 3. And what is x of 3? I can write here, x of 3 is equal to the coefficient of the signal, that is 1 by 2j. 1 by 2j. So these 4 are the Fourier series coefficients of the given signal. Okay.